After the amazing start yesterday, we have more nice topic today. So we have the topic. So this morning is Microsoft Innovation Series. We have two talks from Microsoft Research. The first one is from David Foster, who's a senior researcher at Microsoft Engineering. And so we talk about statistical complexity. I personally wanted to hear about this, so I got him to talk about it. Thank you, sir.
Great. Let's see. Yeah. Okay. It sounds like the audio is working. Hopefully, everyone can hear me. I'll go ahead and dive in. Yeah. So this is a talk about what I'm calling interactive decision making. You know, kind of in line with the theme of the workshop. But let me just make sure we're on the same page about what I mean by this, right? So when I say interactive decision making, I'm thinking about problems where we're, interacting with an unknown environment, and trying to make decisions on the fly, like, what signal do I send to my robot's actuator, or, what treatment do I give to a patient? And I'm really thinking about problems where we want to do this in a data-driven fashion. Like we want to learn to model the environment better and better so that we can improve our decisions as we go. So, interactive decision making, this is a very broad problem. There's all sorts of different ways you can try to formulate and attack this depending on the problem domain, right? We have these formulations like contextual bandits. They're widely used in online recommendation. We have these more general formulations like reinforcement learning and control that have been applied throughout robotics. And there are all sorts of very other interesting formulations that we see across operations research and let's say personalized medicine. And so, the question we're going to try to explore in this talk is, given that we have all these different ways of, formulating and trying to solve the interactive decision-making problem, can we get something like a unified approach to, designing algorithms and understanding sample complexity and statistical considerations? This way we don't have to necessarily start from scratch every time we're faced with a new problem domain. And so, with that in mind, the game plan is going to be, so I'll start by formally introducing, the interactive decision-making problem and kind of highlighting some challenges. Then we're going to introduce a new way of trying to solve this. And we'll see how this, leads to kind of new algorithms and sample complexity guarantees through a bunch of illustrative examples. So let's just go ahead and dive in. Okay, so for this talk, because I want to be able to kind of, look at many different decision-making problems, it'll be helpful to adopt a kind of general language for talking about these decision-making problems, which we call, decision-making with structured observations. And again, this is really just a simple kind of let's say unified language. So the way this is going to work is we're going to play for capital T rounds, where at each round, little t, we're first going to select a decision pi t. So big pi here is our decision space. And then based on this decision, we're going to get some kind of reward. And we're also going to see some kind of auxiliary observation. And our goal is just to learn to maximize this reward as we go. So if you worked on bandit problems, this should look pretty familiar. I'll show in a second that kind of the added generality we have here actually allows us to encompass things like reinforcement learning. But first, I need to get through a few more details on the setup. So first of all, we're going to consider a stochastic version of this setting. So this means that we have what's called an underlying model M star, which is just like a conditional distribution over rewards and observations for the decision we pick. So what we're assuming is at each time t, when we pick our decision pi t, this reward and this observation are drawn independently from this conditional distribution M star of pi t. Okay, so we don't know M star in this setting. This represents the environment and this is unknown. But we're going to assume that it belongs to some known class, script M, which we're going to call our model class in this talk. And this is something you can think of as, encoding our prior knowledge about the problem we're trying to solve, in a similar fashion to how a hypothesis class would encode our prior knowledge about the prediction task we're trying to solve if we were doing supervised learning. Okay, and the last detail to mention here is we're going to be measuring performance through regret. Okay, so regret here is just, the difference between the cumulative reward of the best decision we could have picked if we knew the underlying model M star minus the cumulative reward that our learning agent actually achieves. Okay, and just a note on notation here. So FM of pi here is just going to denote the expected reward of pi if M is the underlying model. So FM star here is just like the, the mean reward function for M star. Okay, and pi star, yeah, is just the optimal decision for M star. Yeah, question?
What do you mean by structured observations here?
Well, I just mean this observation, but let's actually go through some examples to make this more concrete, because this is a great question. Yeah.
Just to clarify, by making it independent, are you eliminating RM?
No. So this will encompass, let's say like episodic RL settings. It wouldn't necessarily encompass single trajectory RL settings. But yeah, I'll go through some examples and we'll make this more concrete. So okay, the most basic example you can think about here is multi-armed bandits. This is just this classic setting where each time I pick a discrete decision, I get some reward for this decision. I don't see what reward I would have gotten if I picked a different decision. So in this context, we have no observations besides the rewards. Our decision space is just going to be a finite set 1 through big A. And we're not really going to assume anything about the reward. So we'll just say like, script M is like, all possible reward distributions, maybe with some like basic regularity assumptions like being bounded. Okay. Yeah, now, as I said, okay, Bandits is a setting where we don't typically assume much about the rewards, but it is a setting where we usually have to have like a small finite set of actions or decisions. By incorporating more modeling into your problem, you can tackle problems where you have maybe a very large or continuous set of decisions. So linear bandits is a setting where, let's say our decision space is some subset of R to the D, but we assume the rewards are linear, which kind of allows you to extrapolate, right? And the way you can encompass this is just by saying, I'm going to restrict script M to only have models that have, linear reward functions, right? That's pretty natural. And of course, there's many variants of this you can look at, so like non-parametric bandits, this is a more general problem where you, let's say, only assume the rewards are Lipschitz. Again, the way you're going to encompass this is just by saying all the models in my class have Lipschitz rewards. Okay, now I haven't said anything about observations yet, but like, okay, so let's look at the canonical, setting we like to think about where these matter. This is going to be episodic reinforcement learning. So in this setting, each model is going to be a finite horizon MDP. So this is going to have a state space script S, an action space script A probability transition distribution PM, a reward distribution RM, and an initial state distribution D1. Okay. So how is this going to work? So the way an episode in one of these MDPs is going to work will be that we'll draw the initial state S1 from this initial state distribution. Then for each step, little h equals 1 through big H, we'll pick an action using some policy that acts on the current state. We'll see a reward based on the current state in action, and we'll see we'll transition to the next state also based on the current state in action. So how do you view this in our general framework? Well, that's one episode, but when we look at this in the general framework, we're going to be playing capital T episodes. So at each time step, our decision is like, what policy do we play for the episode? The observation here is going to be the trajectory that this policy gives us. So this like sequence of actions, states, actions, and rewards. And the reward function we'll be aiming to optimize is just like the cumulative reward within each episode. Okay, so that's kind of that's a simple way of viewing RL in this framework, at least episodic RL. And one thing I want to emphasize here is, there's a huge amount of flexibility in how you do modeling here. So like in this setting, your model class script M, this is parameterizing, like what are the transition probabilities? What are the reward distributions? Like what constraints are you going to put on these things? And there's all sorts of structures that have been investigated here, both like classically and in the last decade, right? So, there's simple things like finite states and actions, like tabular MDPs, there's like linear dynamical systems, but there's, there's a lot out there. Okay, and so kind of just to get back to the main point here, the reason we adopted this general decision-making framework is just that this gives a concise way of talking about what you can see is like a pretty broad class of problems with many options as far as how you do modeling. Now, okay, in general, what sort of modeling assumptions, like what model class script M works well for your problem, this is going to be very domain or like application specific. And so what this is going to lead us to ask here is, can we have something like, a unifying notion of problem complexity, or say like statistical complexity that can, will capture the optimal complexity for any problem. And really when I say optimal statistical complexity here, what I mean is like, what is the best regret we can achieve for a given model class script M and a given time horizon T. And kind of the hope here is, we had such a notion of problem complexity, maybe this could guide us in designing algorithms when we encounter new domains so that we don't necessarily have to start from scratch. Like, this could guide us towards like general algorithmic principles. Okay, so to motivate our results, I want to try to give a sense for like, why this is a challenging problem, like why understanding and, capturing the statistical complexity for general decision-making problems is challenging. And kind of the key point here is this is really a combination of like algorithmic and statistical considerations. These are really like intertwined. And the way I want to try to illustrate this is just by going through a few examples of different models and trying to get a sense for, well, like what makes these problems easy versus hard. Okay, so let's start on that. Okay, here's a kind of bandit type problem. So we only have rewards here. We only see rewards. There's no other observations. Our goal is just to maximize like the underlying reward function. And what we have here is a model class with like 3 models, M1, M2, and M3. And this plot over here is just looking at like, their mean reward function over the decision space. So, okay, so this is what I'll call like a very easy or actually trivial decision-making problem. Okay, so, if I tell you that the true model lies in this class script M in advance, well, what you can see is like actually all these models, even though they have different reward functions, they all agree on what the optimal decision is. Like they all peak at the same place. Okay, so if someone tells you in advance, the underlying model is in this class, well, I can just commit to playing this one point in advance. I don't need to explore or really like do anything at all. Like the algorithm is just play this point, you're done. Okay, so that's like kind of the easiest problem you could hope for. Let's change this a little bit. Okay, so now I've moved these curves around and we've got, let's say 3 distinct peaks for these different models. Okay, and so now this is a little bit harder. Like now if I want to try to maximize the reward function and I don't know what the underlying model is, I do need to actually like explore the domain to try to find like where the peak is. And in general, the number of samples you need to do this, or like the best regret you can achieve, this will scale with like the number of possible peaks or like, how big your domain or your decision space is. So that's a slightly harder problem. Okay, but now I'm going to change this one more time. Okay, so this is almost the same. We still have different peaks, but then if we come over on the right here, what's going on? Well, I have kind of one very informative point in the domain right here where I know that these models all take very different values if we look at the reward function. Okay, so now if I know in advance that the true model is in this class, what I can do is just play this decision right here a bunch of times, get a good estimate for the reward at this one point, and from this I can just infer what the underlying curve is and just hop over to the optimal solution because I know it's one of these 3 models. So kind of again, just by changing this problem very slightly, I've ended up in a setting where I don't really need to explore at all. Okay, so to kind of summarize the takeaways here, if we want to understand what is the statistical complexity of decision making, there's a bunch of considerations we have to look at, right? Like, do we have many optimal decisions or few optimal decisions? Does a given decision tell us something just about the reward at this one point or about like the whole domain? And the point I want to emphasize again is, this really is like an algorithmic problem, right? So like for the examples we just saw, okay, they had different statistical complexity, but the strategies we had to use to achieve this were very different, right? It wasn't like we were just, fixing some algorithm like, ERM or SGD and just trying to understand like how well it performs when we change the underlying problem, like you might do in say like supervised or statistical learning. And just to drill on this even more, so for the examples we just went over, we were really only looking at mean rewards, but these challenges kind of only get amplified when we look at more general problems. So like in general, even things like the noise in the reward distribution can like leak non-trivial information about the underlying problem instance, and algorithms can exploit this to do better, right? Like, so for example, if you have like a bandit type problem and I say, the optimal decision always has Bernoulli rewards, all the other decisions have Gaussian rewards, Like that is something that algorithms can exploit to do better. And so any notion of problem complexity needs to be able to capture this. And of course, these are only amplified when we look at these problems like RL, where we have decision spaces and observation spaces, that are very high dimensional, but also very structured. And so in light of these challenges, I think it's natural to ask, is it even reasonable to hope for some like single notion of problem complexity that can, adapt to all these different settings, at least in a way that's like meaningful or like, let's say like useful or actually interpretable. But what I'm going to show now, is the answer is in some sense, at least we think yes. So we have a kind of a new notion of statistical complexity that is necessary and sufficient for low regret in these general decision-making settings. And beyond just giving a unified notion of statistical complexity, this is actually going to come with something like a unified algorithm design principle. Okay, so I'm going to just dive into this. So this complexity measure we call this the decision estimation coefficient. And I'm displaying this right here. Okay, so there's many moving parts here, but we're going to like walk through this step by step and kind of like build some intuition for what's going on. So this decision estimation coefficient, or like I'll call it the DEC for short. So this is going to have 3 parameters. Naturally, it's going to depend on this model class script M. It's going to depend on what we'll call a reference model, M bar, in this class. And it's going to depend on a scale parameter that we call gamma. So let's walk through this. So I'll start by, I'll walk through it once, and then I'll walk through it again to make sure everyone's on the same page. So this is a min-max problem. This DEC is a min-max problem. It's a min-max problem where the min player, which you can kind of think of as like representing the learner, is trying to pick a distribution over decisions such that for a worst case model in this class script M selected by the max player, what they want is to have their sort of instantaneous regret or like instantaneous suboptimality under this model to be balanced by a notion of like information gain for the decision they selected. Okay, so here, what do I mean by information gain? So what we're looking at here is for the decision pi we sample here, what is the distance between the distribution over rewards and observations under this reference model and the distribution over rewards and observations under the model selected by the max player? And here we're using Hellinger distance, which is this like information theoretic divergence. But you can think of KL if this is more familiar to you. The difference will not be important for the results I'm presenting. But this is this is saying, information gain, if you want this to be large, you want to be selecting a decision where these 2 models, have very different distributions, right? This means that, even if I didn't necessarily make my reward big, I've kind of learned something about which of the underlying models it was. Okay. So, okay, that was a kind of a mouthful, but let me just say this a little more succinctly. So this is a min-max problem where the learner is trying to select a distribution over decisions such that in the face of an unknown environment, they want their regret to be balanced by, information gain, which I think is pretty natural. The parameter gamma here is just kind of modulating this trade-off. Like how much do you care about regret versus information gain? Okay, just a note here. What we're actually going to care about here is the max of this thing over all reference models. And again, so why do we care about this? Well, what I'll show you now is this leads to, okay, both upper and lower bounds on regret for decision-making problems. And I'll start with like the lower bounds, just kind of a teaser for the lower bounds. So what you can show is that for any model class, script M, the best regret that can be achieved by any algorithm is always lower bounded by the DEC for an appropriate choice of this parameter gamma. And kind of the short version of the story here is, you can use this to recover, like the usual lower bounds for kind of all the standard bandit and like RL settings that you might see studied in the literature. up to like, let's say, small Pauli factors and perhaps some other small technical caveats. So everything in this table, these are all just like special cases of this general lower bound based on the DEC. And a point I really want to emphasize here, or something, well, that I personally think is pretty cool is, this is not just recovering lower bounds for like, problems like the bandit that we know are tractable. This can also recover even things like exponential lower bounds or like intractability results for like, RL problems that are known to be intractable, like where the optimal sample complexity is exponentially large, which I think is pretty cool. Yeah. Yeah.
You're saying the DC will evaluate to those things?
Yeah, when you pick gamma appropriately. And I'll give a little bit more insight into how do you pick gamma. Yeah, in a minute. Yep.
Why the square Hellinger distance?
Versus
special about this particular.
Oh, I mean, no, it's not super special compared to like, let's say like KL. Like the difference between these things is like, I would say more or less for technical reasons.
And the bounds on the next page, are they using the Hellinger distance?
Yeah, so I'm saying you can get all of these using Hellinger or KL unless you like really care about log factors.
And the connection between this and T is like.
Yeah. So the full lower bound is going to involve this thing and T in a way that like, where you're trading these off based on gamma and you kind of pick gamma to trade these off. I'll get to this in like 2 slides. Cool. Okay, now, before I get to that, I just want to give a teaser for the upper bounds. So on the upper bound side, there's kind of a simple algorithmic principle associated with the DEC. We call this estimation to decisions. And the way to think about this is as like a meta algorithm that kind of lets you lift algorithms for supervised learning or estimation into algorithms that can solve the decision-making problem. So the way this is going to work is, okay, we're going for capital T steps. At each time little t, first I'm going to run some kind of like supervised estimation or like learning algorithm on all the data I've gathered up to this point, which is going to give me like an estimator m hat t for the underlying model. So this can be any algorithm you want, but for concreteness, you can think of like, let's say like MLE or like least squares. And once we have this estimator, so all we're going to do is plug this into the min-max problem in the DEC, just as sort of the reference model. We're going to pick the PT that solves this min-max problem. And then we're just going to sample the decision to play from this distribution and update this supervised estimation algorithm with the new data point we collect by doing this. So what you can show for this strategy is it's going to make it so that your regret is controlled by this DEC and some term that's going to reflect how well are you doing at estimation. More precisely, we're going to define est Hell of T. This is going to be just the cumulative Hellinger distance over all rounds, let's say little one or T equals 1 through T of the Hellinger distance between the estimator we had at round T and the true model M star on the particular pi T we encounter. And so what this theorem says is if we run E2D with scale gamma, our regret is bounded by DEC at scale gamma times T plus gamma times this estimation error. And a point I want to emphasize here is, okay, so this estimation, this is kind of like a sequential problem where we're trying to do estimation on data that's collected adaptively based on the decisions our algorithm selects. But this is actually something you can like provably control. Like you can provably get sublinear bounds on this using tools for online learning or like sequential prediction, right? So the point here is, if you just kind of use standard online learning tools, you can get bounds on this Hellinger distance, that reflects just like the intrinsic kind of statistical capacity of this class script M. So for example, if I have a finite class, I can get like log number of models. If I have a parametric class, I can get something like dimension. To interpret this bound though, it's actually going to be helpful to look at this again side by side with a more precise version of the lower bound. So this is going to be the main lower bound, and this is going to say, okay, under appropriate technical conditions, for any model class script M, the best regret that can be achieved by any algorithm is going to be lower bounded by the min of 2 quantities. One is this DEC at scale gamma times T. The other is gamma. and then you're taking the max over gamma. So, intuitively, this is going to say, if the DEC is large, your regret has to be large. But the cool thing here is if you run a slightly more refined version of this E2D algorithm, you can get a regret bound that matches this up to the dependence on this Hellinger estimation error. So this is saying up to whatever the estimation rate for your class is, you're getting these upper and lower bounds that kind of quantitatively match. Okay, and let me finally give an example to get a sense for the scaling here. We're going to go through many more of these in a minute. If we look at something like, say, the multi-armed bandit with A actions, we'll be able to show that the DEC at scale gamma is A over gamma. You plug this into this lower bound, you get, okay, min of AT over gamma, and gamma, the right choice of gamma here is going to balance these quantities, and this is going to give you root AT as the lower bound, which is the usual minimax rate for this problem. And this, like I said, we'll see more examples, but this sort of scaling where you have some notion of complexity over gamma, this is very common. So yeah. Yeah, I'm not being precise about this. So this is going to be, okay, I can go into more detail about this offline, but this is going to be basically DEC for a ball around M bar, where the ball depends on some parameter epsilon gamma, which depends on gamma. It's a little more technical. Yeah. I have some bonus slides we can go over if there's interest in this after. Yeah. This is not something that really matters for any of the standard problems you would look at. This is kind of only something that matters for what I would call edge cases. Okay. Now let me zoom out for a minute before I get to more examples. So kind of the point here is because you have these upper and lower bounds which are matching up to this estimation error, you can actually really get from this a characterization for learnability. So when is learning possible at all? And this is going to say okay, if under appropriate conditions, you can have sublinear regret if and only if this DEC decays polynomially as a function of gamma. And that's why we say this is necessary and sufficient. Let me make some technical remarks before I move on. Okay, so first of all, okay, to answer this question of why Hellinger distance, yeah, so this is not super important compared to other information theoretic divergences. As long as you make pretty mild assumptions on the densities that they're bounded above, you can get essentially the same results up to log p factors. The Hellinger just kind of is the choice to make that makes the upper and lower bounds kind of as clean as possible simultaneously, is the way I would describe this. Okay. And yeah, let me also just give a technical disclaimer here and say, I've really only presented informal results so far. There are different gaps between the upper and lower bounds depending on exactly what you assume. And yeah, happy to say more about this online or offline. Okay, let me zoom out and just give a couple conceptual takeaways here. So first of all, one thing that I find exciting about this is it really kind of gives a way of kind of what I would describe as bridging the gap between learning and decision making. So the point is we have supervised learning, which is this seemingly passive problem, and then we have decision making, which is this very sequential and active problem. But this is saying as long as you can do this estimation part well, as long as you can do learning well, you really can lift this into algorithms that solve decision making. And this really gives you a tool that allows you to focus on really more modeling and estimation when you're faced with new domains rather than algorithm design. Okay, the other takeaway I want to mention here is a connection to kind of classical results in statistical estimation and Lecombe theory. So if you're coming from the stat side, you might be familiar with this notion of modulus of continuity in statistical estimation. This is a complexity measure that was introduced by Donahoe and Liu in the 80s for non-parametric estimation, which is just looking at this problem where I get a bunch of IID examples from some distribution, and I want to estimate some kind of functional of this distribution. And I'll just show this modulus of continuity right here. So here for this setting, okay, I've kind of written it in the same language as this general decision-making setting to emphasize the similarities. Here, models are just going to be distributions over samples, everything is IID. FM is the functional we want to estimate. And this is just saying, if we look at the Hellinger ball around some reference model, like what's the biggest error in the value of functionals? So what Donahoe and Liu showed is that this lower bounds the optimal risk for any non-parametric estimation problem. It also gives upper bounds under various technical assumptions. And the point here is, we really think of the DEC as giving like the decision making analog of this complexity measure and kind of a way of lifting this kind of, like statistical estimation, Lacombe viewpoint to general decision-making settings. But the difference and like what really makes sort of the decision-making version challenging is like, because everything is active now, this is why we have like a min-max problem rather than just a max problem. This is one way of saying it. Yeah, and actually just while we're on this topic, I'll just briefly mention, there's a couple other complexity measures you may have seen before, more on the decision-making side that also kind of look at different trade-offs between regret and information. I'll just say you can check out the paper if you want to understand more about like how you can relate these to the DEC or when you can and cannot. Let's see, are there any questions before I move on? Yeah.
So when you first showed the bound, I thought like the first term was capturing some information, and the second term was estimation. But then like when you showed the statistical estimation result, they probably are not capturing the exploration.
Yeah, well, that's exactly right. This modulus of continuity, it's not really capturing exploration. All it's really capturing is like, suppose I've done estimation well. What is the most that I can like mess up? Like I've estimated the model as well as I can. So I have some sort of uncertainty set that remains given that I've done this. So like in the worst case, just like what's the worst I can screw up?
It's probably capturing the second term.
Not quite. It's closer to the first term.
Okay.
Yeah.
That's what I'm confused about. But isn't the first term capturing?
Right. So the difference is like, what are you estimating? So the point is, in this general functional estimation setting, so the second term is how well do you underestimate the underlying distribution, and then the first term is capturing, like, you don't actually care about estimating the underlying distribution. You care about estimating some function of it. So this is capturing, what is the error you pay in going from estimating the distribution to estimating this functional. That's kind of why they call it the modulus of continuity. It's kind of trying to capture how continuous is this functional with respect to the estimation error.
It's kind of the condition.
Yeah, kind of. Yeah, more or less. Okay, cool. Yeah, so for the last part of the talk, I just want to go through a bunch of different examples and just give a sense of like, how does this DEC behave? How do these bounds behave when we instantiate it, right? And like, what do the like minimizers, like what do the distributions that solve this minimax problem actually look like? And so we'll go through a few different types of examples. The first are going to capture just, how does this thing adapt to different structure in the reward function? Then we're going to go through an example that's a bit more information theoretic in nature. And then we'll kind of bring observations into the picture and look at tabular RL. And to the extent that there's time after that, I'll try to give a sense for what this looks like when we go to more general RL settings as well. Okay, so for the first example, I'll come back to the multi-armed bandit problem, right? Just finite set of actions. And for this problem, I'm displaying the full DEC here. But actually what you can do is simplify this to a kind of a variant of the DEC where you just replace Hellinger distance by squared distance between the means. These are actually equivalent for this setting. And the intuition is just that like, okay, if I don't really assume anything about the noise, then in the worst case, the max player here can just pick like white noise, which makes everything other than the means like uninformative. Okay, so as I mentioned before, you can show a bound on the DEC that looks like A over gamma here. This gives like a root AT lower bound. But what I want to do is kind of give a sense for like, how do we actually get this? Well, how do we bound the DEC by A over gamma for this setting? And there's two strategies we'll look at. So the first strategy is what's called inverse gap weighting. This is going to be like an explicit distribution P that kind of solves this minimax problem. And what this looks like is, okay, given that I have this reference model M bar, this parameter gamma, I'm going to assign each decision pi a probability that's inversely proportional to the gap between sort of the optimal decisions reward and this decision pi's own reward under this estimated model M bar. This gap is going to, okay, so first of all, I'll just say, okay, so the probability is inversely proportional to the gap. That's why we call this inverse gap weighting. But this is going to be scaled by the parameter gamma. And then we're going to pick a normalization constant lambda that makes this thing sum to 1. So you can show that this thing exactly minimizes the DEC I showed on the previous page. This is like a pretty easy calculation. This is just, you pull out the Lagrange multipliers and turn the crank. And this is going to lead to an A over gamma bound. And kind of the intuition here is like, okay, if I take gamma to 0, this just becomes the uniform distribution. If I take gamma to infinity, this just puts all its mass on this like greedy decision. But in general, it's going to kind of adaptively, interpolate between exploring and exploiting in a way that depends on the estimated rewards. And one point I want to emphasize here is like, I think that intuition is pretty clear, but like the specific structure of the distribution here, is pretty important. Like, trying to do similar things with like, say, softmax is not going to work. Like the kind of key thing here is this distribution is really kind of like heavy-tailed in a sense. Okay, that's one approach. The other approach we can look at is to appeal to Bayesian methods. And okay, when I say this, you might say like, well, okay, how do we do that? Like I've been only working in a frequentist setting up until this point. But the idea is there's a Bayesian counterpart of this DEC that we can show is equivalent to the original one using the Minimax theorem. So the idea is you can move from a max over models here to a max over distributions over models. That makes this thing like bilinear in P and this model distribution mu. So you can apply the Minimax theorem to make the max player go first. And the interpretation here is now the max player is picking like a prior over models. And the min player is able to choose their decision distribution with knowledge of this prior. So they're trying to make this inequality hold in expectation under the model being drawn from the prior. And so once you have this Bayesian version of the DEC, you can appeal to kind of natural Bayesian algorithms like, say, posterior sampling or like probability matching, right? So posterior sampling in this context will just be this strategy where we take P to be the distribution induced by sampling a model from the prior and like playing the optimal decision for this model. And you can show this also leads to a bound of like A over gamma on the DEC here. So I think that's a pretty cool connection. And sort of the point I want to mention here is, okay, like why did I show these two approaches? Both of these turn out to be very useful in analyzing this thing. Like when we go pretty far beyond just the bandit setting, so even to like RL settings. So these are good tools to have in your toolbox. Okay, I'll go to another example here. So this is just going to be full information online learning. This is going to be a setting just like bandits. We have a finite decision set, but now we're going to see an observation, which will just be rewards for all of the possible decisions we could have selected, right? So there's no more bandit feedback. We get to see everyone's reward. So if you compute the DEC in this setting, it still is going to have some kind of like 1 over gamma scaling, but there's not going to be any dependence on A, the number of actions. So this will just lead to like a root T lower bound. And this is pretty natural, right? Like as soon as you get to see all the rewards, sort of the distance between the different models you look at, this no longer depends on what distribution or what decision you pick. So you don't need to explore it all. Okay, now, yeah.
For the full information setting.
Yeah.
Instantiate your algorithm. You had this algorithm, right? So reduction to supervised learning.
Oh, yeah.
So could you explain what that algorithm is doing?
Oh, yeah. I mean, for full information learning, this will sort of be like the most trivial version of this whole thing, right? It's just going to be at each time do the estimation. Okay, so run some supervised estimation algorithm, get an estimator, compute the optimal decision for this estimator, like what decision maximizes rewards under my estimated model, and just play this, right? So like this is just greedy.
But don't we know that doesn't work?
Well, no, so it doesn't work for bandits. For full information, this works. Just to be clear, this is like a stochastic full information setting, right? It's not like I'm not doing adversarial bandits, right? So because it's stochastic, like greedy does work. Yeah. So now I want to look at an example which is kind of in between bandits and full information. And this is just to come back to structured bandits, where we're doing bandits with a potentially large decision space, but assuming different structure like linearity on the rewards. So if you do linear rewards, you can show that the DEC scales as like D over gamma, where D is like the dimension of the action space or feature dimension. This is going to lead to a root DT lower bound. And the way you prove this is using, very similar tools to what I showed for the bandit case. You just kind of combine this with like sort of a notion of like well-chosen basis for exploration. Yeah.
But just to go back to the full information.
Yeah.
So this is in the min-max setting, right? Otherwise, I can get much lower, better bounds are instance dependency.
Yeah, for sure.
Okay.
Yeah. Yeah, everything in this talk is minimax. Cool. So one point I want to mention here about the structured bandits is, this is another example where this DEC is growing at something like, some notion of like effective dimension for the problem over gamma. And you see this in a lot of settings, but in general, you're not going to see this behavior for problems where like the optimal weights are worse than root T. So for example, if we go back to like Lipschitz bandits, which is this non-parametric setting, here you can show the DEC, roughly grows as like 1 over gamma to the 1 over D. So this is getting slower as D grows. And this leads to a lower bound on regret that looks like T to the D plus 1 over D plus 2. Okay, so that's like the optimal rate. But yeah, this is getting worse and worse and worse as you take D big. It's a non-parametric problem. Okay, so for those examples, only reward mattered. Let's look at a very simple example where like, say properties like the noise will matter. This will kind of illustrate why you would need like something like an information theoretic divergence if you want to work with general problems. So let's look at a bandit type setting where we've got A actions. But now the way I'm going to set up the models in my class is to say, okay, if I pick the optimal action for a given model, so each model will only have one optimal action. But if I pick the optimal action, I see a reward that's like Bernoulli with mean 1/2 plus epsilon, so a little more than 1/2. If I pick a suboptimal action, I get Gaussian with reward 1/2. So this is a very easy problem. This is easier than a regular bandit problem because, if I pick the optimal decision, I'm going to see either 0 or 1 as the reward, like almost surely. And if I pick a suboptimal action, which has Gaussian rewards, I will not see reward 0 or 1 almost surely. So all I need to do is like do a single pass over the arms and, commit to the arm for which I see either 0 or 1 as the reward. Right. So this is a kind of silly problem, but like, if you want to be able to capture general problems, you do need to be able to kind of handle this type of structure. But what you can show here is, so the DEC is actually going to have threshold behavior. So it's going to be like constant if gamma is smaller than the number of actions. It's going to go to 0 when gamma is bigger. This is just going to lead to a lower bound on regret that scales as like A. So no real T dependence. And this just reflects the fact that you can do this kind of silly strategy I just described. Okay, and the point I want to emphasize here is like, the choice of an information theoretic divergence is important. So like Hellinger or KL, can both instantly tell the difference between like Bernoulli and Gaussian. If you have just squared error between the rewards, this cannot tell the difference. If you have squared error, this looks like a regular bandit problem. And a point that I think is good to emphasize here is, you can take this idea of like problems where the noise encodes information like very far. So you can think about like bandit problems that have Gaussian rewards, but actually if I go like 100 bits down into like the binary representation for the reward, I've gone and encoded some like arbitrary piece of like side information, which like doesn't really change the reward functions at all. But like, again, if you know this in advance, this is something you can take advantage of. So you can kind of use this to encode arbitrary observations. And just to tie this back to the beginning, like the reason why we work in this model where you explicitly get observations, is just to make this explicit, because it's useful to be able to handle observations. And so with that in mind, let's go to the canonical example where these matter, which is tabular RL. So just to recap, we're going to be looking at a model class where each of these models is an MDP with horizon H. We've got finite states and actions, so S states and A actions. Pi is just a set of like policies that act on the MDP, and the observations are just like trajectories that we get by executing these policies. So On the lower bound side, you can show that the DEC for this setting grows as like HSA over gamma. So just like, if I'm in this unstructured RL setting, just these features like the time horizon, the number of states, the number of actions, these are kind of reflecting the complexity. This gives you a root HSAT lower bound. On the upper bound side, you can show similar upper bounds, although with worse dependence on H, using a couple of different strategies. One is kind of an extension of this inverse gap weighting idea that we call policy cover inverse gap weighting. And the other is, to kind of appeal to the Bayesian counterpart of the DEC and apply posterior sampling. So these both give like poly H times SA over gamma. And just like, this is kind of a trivial observation, but just a point I want to mention here is, incorporating the observations in this setting is critical, right? So like if I do RL, but I only see rewards and no trajectories, you do need to pay like for exponential in the horizon. Like this is not a tractable problem. So you really need to be able to see the trajectories to do credit assignment. Okay, and I'll just say a little tiny bit more about this policy cover inverse gap weighting strategy because, well, it just gives us a kind of sense for like how you can take this inverse gap weighting technique to, richer decision-making problems beyond bandits. And the idea will be to, basically do the same strategy as I did for bandits in policy space. The challenge is just like, if I try to naively do this for every single policy, like naively do this inverse gap weighting for every single policy, this will have very bad sample complexity because it doesn't really take advantage of the fact that you can like share information between policies, and there's a lot of policies. So the idea will be instead, we'll do it to a small set of representative policies. And that's going to look like the following. So again, let's fix the reference model M bar. This is going to be an MDP, and this parameter gamma. And for each HSA tuple, we're going to compute kind of what we'll call something like a homing policy pi HSA. This is going to be a policy that maximizes the ratio of two terms. So one is the probability that we like hit state S and action A at step H. That's where the HSA come in. And then on the denominator, we're going to have just the suboptimality of this policy in the reference model. So this is trying to balance, hitting states that you care about, but not making your regret too big while you do this. The way you get your policy cover is just to compute this homing policy for every HSA, put these all together, and also put just like the greedy policy in this set. Once you have this policy cover, you just do the same strategy for bandits, but only to the policies in the policy cover, and that's it. So kind of the key ideas here are, this is balancing like exploration or like covering the MDP by, considering this hitting probability in the numerator, but it's also making sure we're not visiting states that just have like very bad reward, right? Which is not good for regret. And the real subtlety here is just like, what we really care about is covering on like the true MDP M star and not on M bar. But using kind of change of measure type arguments, you can show that like, when you run this strategy, like one of two things happens. One is that like, M star and M bar behave similarly, in which case this does give good coverage. The other case is they don't behave similarly, but that means your information gain must be big, which is also good. Okay, we're just about at the end. I'm going to give a very quick taste for what happens in more general RL settings. So, when I talk about more general RL settings, like going beyond tabular, really what we have in mind is like handling large state spaces. And, this entails, using function approximation and modeling in a way that will allow us to like kind of generalize or extrapolate across, states that we might not have seen before. And there's a few different ways that you can apply the idea of modeling in this setting, right? So one idea is just to explicitly use what people usually call model-based methods. And this just refers to methods where script M is like directly parameterizing the transition dynamics. So if you look at like, say, like linear systems, like the LQR problem, this just means like M is parameterizing like what are the transition matrices, like what are the system matrices. Those are kind of model-based methods. And you can also look at value-based methods. So for value-based methods, there's not usually an explicit model class. Instead, you have something like a value function class, which I'm calling script Q here, which is just trying to model the Q functions for your MDP, right? So these functions that say, if I'm in state S and take action A and then run this policy, like what's the expected return? So yeah, so for these settings, I'm usually just modeling the Q functions, but you can still like apply the results we have in these settings by just working with an induced model class. And this is just going to be the set of all MDPs that are like consistent with your Q function class, in the sense that like, you know, maybe their Q star functions are contained in this class, maybe like all Q functions are contained in the class. That depends. You can do either. So, you know, there's many examples of both of these, you know, approaches. You know, this is a pretty, I would say, active area of research right now. And there's also a bunch of kind of like general notions of like problem complexity or like structural complexity that kind of give sufficient conditions that kind of try to encompass all these different individual settings that we know are tractable. So like you may have seen Bellman rank before. This is a very famous one. And so what you can show is that for all of these, you can use these to bound the DEC. So if you look at Bellman rank, for example, you know, you get something like DEC scales as Bellman rank over gamma. That's cool. One caveat here is this does not always lead to end-to-end guarantees right now, because the estimation complexity can actually be quite large for some of these settings. So this is an interesting future question. But so that's like upper bounds. And I'll just give a taste. You can also get upper bounds. So for example, there's like a sort of like very, at this point, I would say famous line of work from like Chauba's group that shows that, you know, if you try to do like RL with linear function approximation, and you're not careful about how you set this up, you can get, say, like exponential sample complexity, which is not good. And you can recover these lower bounds through the DEC. All right, so I'm actually just at the end now. So I'm going to go ahead and summarize. So, okay, we saw in this DEC, this complexity measure, this is necessary and sufficient for low regret. But yeah, personally, what I find exciting is, you know, this really gives kind of something like a unified handle that you can use to study algorithm design when you encounter new settings. In terms of future directions, I think there's a lot of very interesting ones. One I'll just mention first is on the practical side. So if you specialize this all to the case of like Horizon 1, so like contextual bandits, we've actually already seen that the algorithms that come out of this framework are like very practical and even have like state-of-the-art performance. And I'm just giving a teaser here, but like, yeah, these are actually already in this like VW library for kind of online and like interactive machine learning. So, you know, if you want to like run these and try them out, it's very easy to get sort of get this started. But I think when we go beyond Horizon 1, there's room for a lot of investigation in terms of understanding like how can we get, you know, algorithms for RL that really like work in the real world, right? And this is a combination of, I think, well, algorithm design, but also figuring out what kinds of models work well. Okay, and I'll just say a little bit more broadly, you know, the real kind of broader research program here is just trying to like build foundations for these data-driven decision-making settings that kind of give us some kind of understanding that parallels what we have for, you know, these more classical settings like supervised learning or estimation. And this really is not just limited to the setting I went over in the talk today. So I think there's, you know, a huge amount of opportunity here in like understanding how can we do similar things for like, you know, learning with logged data, learning in like multi-agent settings. And these are questions I'm thinking about a lot right now. And of course, there's many open technical questions with people like this sort of thing. So happy to chat about those more offline, but I'll stop there and take questions. Yes, Kevin.
Seems like the DEC is, it kind of comes down to like parameter counting, at least at a very, very high level. But like the estimation part, where you're like looking into like, you know, the union bound type stuff, actually estimating that.
Yeah.
It only appears in upper bound, right?
Yes.
Have you gotten any closer to showing that in a lower bound?
I would say no, but I also haven't been trying that hard. Yeah, so this is an interesting problem, like in the sense of like understanding what is the minimal notion of estimation you have to do in some sense. And what's subtle is like, if you want to get the tightest possible results, you cannot fully like decouple these things. Like there are some problems where the estimation error should not be there in the upper bound, and you can just get rid of it. There are other problems where it should be there, and so the question is, how do you make it appear in the lower bound, right? So like it's not just a question of like, yeah, like I said, it can't be fully decoupled from the decision-making part, and I think that's really interesting. In some sense, like the key question here to me is like, what is like the kind of the minimal sort of like sufficient statistic that you actually have to estimate for a given model class? Like it seems like any model class should like induce a sort of fundamental notion of distance that's like tailored to the model class. So like if you do bandits, like something that automatically pops out of this is like you really don't care about estimating the distribution, you just care about estimating the means. But like that's kind of like an ad hoc calculation that you can do. I don't know of a sort of like systematic way of deducing like what is the right notion of a sufficient statistic for a general problem. But this is like very much related to your question. I think it's super interesting. Oh, yeah.
So I guess like in multiple bandits and in reinforcement learning, we know often that we can get better guarantees than the min-max. And also we know that we can get non-stationary guarantees in the other direction. Can you comment on either direction?
Yes. Okay, so I'll do the second one first. So one natural variant you can do for this is like the adversarial setting. So imagine a setting where instead of there being like a fixed underlying model, an adversary chooses a model class in your model class at each time step. This is something that like encompasses like, adversarial bandit problems, adversarial linear bandit problems, adversarial like bandit convex optimization, whatever you want. So we've actually already extended this stuff to that setting. The algorithms are completely different. But the sort of guarantee you get is same sort of upper and lower bounds, but rather than DEC for the original class, you pay for the DEC of the convex hull of the model class. So like the gap between stochastic and adversarial is like, how does your class behave under like convexification? So, okay, that paper is online. It's called like On the Complexity of Adversarial Decision Making, if people want to Google it. Yeah, for instance dependent, this is a very interesting question. Which Andrew and I have been working on for the last 2 months. So hopefully there should be, the results are like it's quite subtle compared to the Minimax case. But yeah, we made some pretty good progress on this, I think. So, okay, I guess keep an eye out for our head. Oh yeah.
So your deck measure is ultimately defined as a max over reference n bars, right? It seems like in all your examples you're able to do uniformly for all n bars, right? You have to use the max, is that right?
So usually the strategy, or I'll actually say it's like in all cases, the strategy that you use to achieve the minimum depends on the particular n bar you look at. But yeah, you're like usually the way you bound the DEC is just by like figuring out how to bound it for a fixed reference model and then just like taking the max over all these things. Yeah.
But I'm saying like for the bound, like you don't even need the max, right? You're able to get it uniform for all n bars.
You mean for m bars that are like not necessarily in the class, or?
No, right, the class for each bar in the class you're able to get the bound. So you didn't have to do the max to get the bound. It looks like from the examples.
I guess I'm just saying like it's not clear to me why these are different if you're thinking about like upper bounds. Right, like I'm just saying, like saying that this thing is upper bounded uniformly for all models n bar is kind of the same as.
So for the lower bound.
Oh, I see. You're saying for the lower bounds.
Yeah.
Yeah. So usually for the lower bounds, you pick like m bar to be, I would say, kind of like an uninformative model. Like for like bandits or something, you pick it to be like just like flat. But yeah, no, it is true that the lower bounds. I mean, usually these are these are realized for like reasonable looking m bars, but like. I'm not sure I actually fully understood the question.
I think we can take it off.
All right, sounds good. Yeah.
The posterior sampling algorithm that you demonstrated, was that for Bayesian?
Well, so it's for the Bayesian counterpart of the DEC. It's not for like Bayesian regret.
You're right.
So the point is, I can go back to this real quick actually. So yeah, the point is.
Yeah, what do you use as prior is learning?
Right. So the point is, you can show the posterior sampling gives a bound of A over gamma on this thing, like uniformly for all choices of prior.
You can just any mu to believe it.
Yeah.
It at least needs to have support or something.
I mean, it's not important if it has support on LM. I mean, if it has support on a smaller set of actions, okay, you'll get a smaller bound than A over gamma.
But if your prior doesn't have support on the model that the true model, then you will never get to the true model.
This is a setting. This is like a sort of a setting. So again, like this is not like looking at Bayesian regret. This is literally just like this is just an analysis tool, right? So I'm just saying this is a Bayesian, like the DEC is like a one-step game. This is like a Bayesian counterpart of this one-step game. But I'm saying this is a setting where like you have like a well-specified prior in some sense, right? Like the max player picks this mu, and like the kind of true model, as far as this expression is concerned, is like drawn from this prior.
Oh, it's
right?
non-constructive.
Yeah, but yeah, this is an important point here, right? This is like non-constructed in the sense that like this is just a way of proving that this thing is bounded.
It's like the use of Minimax Theorem.
Yeah. Exactly. Yeah. I mean, in a formal sense, that is a special case of this. Yeah. Cool. Are there any other questions? All right, we can leave it there. Yeah, thanks a lot.